Yeah. So I want to give the third introductory part. This part is about models with subpopulations. As mathematicians, we start basically with exactly the same, only each subpopulation gets its own index. And so there are a lot of indices in this case, which sometimes we try to combine to something which we call a matrix. So this is the matrix A now of these infection and cross-infection rates alpha Lj or alpha JL. So what does this mean? The change per time of the ratio of susceptibles in the population, in the subpopulation, which is indexed by L, is proportional to the current level of susceptibles in that subpopulation multiplied with the probability to get infected, and that depends on the total number of infectious individuals in all these subpopulations, but of course weighted with the probability to meet such an individual in the other subpopulation, and that is what I call alpha Lj. It is the probability for an individual in the population L to meet an individual in the population J. And of course, these rates depend on different things, on, let's say, the activity that individuals have, and also about the relative size of the population, obviously. What we will use this later on, I mean, the subpopulations which interest for corona especially are the different age groups. So especially the older age groups, let's say the people who are above 70, usually are assumed to be a little bit less active than the younger people, so they will not have such a high contact rate on the one hand. On the other hand, of course, they will be much more vulnerable to the disease. And so what we would like to do in the end is we would like to devise strategies, obviously, which allow the subpopulation of elderly people to contribute as little as possible to the overall immunity. And I tried. So if you don't, if you are not familiar with all these kind of notation of indices and systems of ODE, it's not so important to look at these formulas which I wrote down, but maybe I will explain a little bit in a much simpler model what is going to happen if you divide a population into two groups. Let's say, with respect to the mechanism of infection, in this case, the population is homogeneous. But what happens then if you have one part of the population, so a fraction lambda, which has a certain risk, and another population and the rest, which has a different risk with respect to this kind of infection. Now, in this particular case, it is easy to write down what these cross-infection rates are, because they just depend on the corresponding fraction of the subpopulations themselves. So I wrote this down here as a in terms of formulas. Of course, it is an absolutely artificial way, from the point of view of the infection itself, to divide the population in two parts. But what you see, of course, is even without looking at this formula, that in such a case, since basically all the stable states are the stable states for just this one homogeneous subpopulation, your choice to reach a stable state, let's say the combined herd immunity, just is kind of dependent on the value that you have here for S1 and S2. And of course, if you want to reduce the risk for the, let's say, for the elderly people, even if they behave the same way that the others do too, what you want to do is, of course, you want to have a high proportion of immune people in the low age group, where this kind of immunization was basically without risk, and you want to have a small proportion of immunization in the group of the elderly people, because for them the risk to die during the infection is of course much higher. And that is what I'm indicating here. So if you understand the formula or not, it's not or don't, it's not of such a big importance. What I will do is I will write down, now I have to erase again, but I will write down one kind of general kind of scheme, what we can say about stable states, mathematically say about stable states for these SIR model with different subpopulations, and that is then the end of the basics of SIR models, and I will come to more to later on to a descriptive way of data. So thank you for that for a moment. I'll be back in no time. Yeah, so there are two facts about these vector SIR models. I call them vector SIR models because I wrote it down as a vector in mathematical terms, this array of percentages of susceptibles in the subpopulation S. So there are two facts about this which make it relatively simple to identify what are the stable states of this system. So in general, basically no assumption at all. When you want to see whether an array of susceptibility percentages S is stable, that means that introducing small numbers of infectious people into the population does not start the epidemic again, then the only thing that you have to do is you have to look at the what I call AS, that is the modified matrix, where here you are multiplying each row by this value of SL. So it depends now, of course, on S. And this modified matrix will have the corresponding the property that either when you are looking now at the discrete process where you are updating with this matrix your entry, your whatever you put in there, you are updating any vector with this matrix discrete number of times, then either this is exponentially contracting or not. Contracting means that eventually the value of the population will go down in this model, but this is not the model that I'm speaking about. It is just what I would say, it's just a mathematically in that sense equivalent model, equivalent only for the question whether S is stable or not. So this kind of a very simple kind of discrete process, which we say, or discrete dynamical system, is a contracting dynamical system if and only if S is stable. And in terms of the matrix, we also say sometimes, for those who have had linear algebra course, what we have to check is just the spectral radius of this matrix with positive entries. So it makes it kind of fairly simple to say in this system when is a state stable and when it is not stable. Now there is another kind of simplification which we have in the particular case that these matrices, we say in mathematics, have a triangular structure, or we could sometimes say that the total system has a recursive structure. So meaning that you can solve recursively first for the population for the population as n, as k, or whatever, and then as k minus 1, etc., etc. So because the evolution of these subpopulations is only depending on those with a higher or smaller index and not the other way around. In that case, whether a state is stable or not stable depends only on the fact that if you look at the subpopulation itself without considering any of the interactions between the other or cross infection rates with the other subpopulations, then this has to be stable for this process, the process which is only taking part in the subpopulation. Now, that is usually, I mean, we don't have this this condition exactly, but we have this condition, I would say, more or less. If you look at the less active part of the population, then this less active part of the population is influencing the more active part with a very small kind of contact rate only. And it is nearly true that we are in this situation here, ALJ equal to 0, when the subpopulation with less activity is, in that case, the population L rather than the population J, indexed by L rather than indexed by J. This is, I mean, the essence of what I want to speak about here. So the idea trying to keep during kind of during the how should I say, during a regime where the immunization takes place via an epidemy, but it takes place in the younger age groups, trying to get the older age groups separated from the younger age groups, and then let the after that, so that is kind of for a given time, for the time of the epidemy itself, but then afterwards the risk for the elderly somehow depends on the contacts between the elderly and does no longer depend on the contacts with the younger ones, where the epidemy has already run its course, so they have already reached their own herd immunity. That's what is going to be the discussion in the next section, and it will be basically completely unmathematical, so it will be a discussion about actual data that we have and why I think that we can reach such an outcome, a desirable outcome for our immunization process. Thank you.